Yeah, thank you for the introduction. I'm super happy to be here. Everybody I met with today, you guys have such an amazing facility. I want to do a couple plugs. We mentioned the Contextual Robotics Institute, so I'm at UCSD. We have an amazing new building, 16 faculty members in a wonderful space. And I want to plug this because I'm recruiting postdocs and PhD students right now for a newly starting project on artificial muscle, amphibious quadrupedal robots. Should be very exciting. The second plug I want to do is we have a new NSF-funded network started on mechanocomputation. So the idea of using sort of mechanical structures to embed computation into robotics and beyond robotics, just physical systems. And so please join our mailing list. I'll put this QR code up at the end as well. We have funding to support yearly workshops as well as travel for students and supporting workshops that you all might want to run. So I'm super excited about this as well. And mechanocomputation sort of fits into the broad themes of my lab's research. I spent 3 years working in a biology lab, actually studying gecko adhesion. That's where I first learned about Mark Kokoski's work and got to work with some of the artificial gecko adhesives that he was building at the time. This was back in 2006, sorry. So I'm just fascinated by biological systems, their ability to work in unstructured environments, to adapt sort of inherently to changing environments with limited sensing and perception, specifically in sort of small scale systems that I find really fascinating. I'm also really interested in robotics as a sort of mechanism to allow us to kind of play with mechanics. I think robotics allow us to ask interesting questions about fun structures and new types of dynamical systems that we can then study and find application for, but also gives us a sort of playful nature for studying these kind of interesting mechanical systems. And today I want to talk about adaptive systems and our work on looking at sort of how we can design systems that display the ability to react, respond, and learn from perturbations to internal and external dynamics. And I approach this from a kind of mechanical design perspective, as well as thinking about simple dynamical systems that display adaptive behavior. And we do this both for sort of purposeful reasons of trying to build robotic systems that have a very specific purpose. And again, I think I want to emphasize the emphasis on kind of play, the things that we can learn from sort of asking questions that don't necessarily have a useful purpose in the beginning, but find their way to working into useful systems in the end. There's kind of three themes that I want to talk about. The first is using compliance to build adaptivity into robotics. Second is using dynamics and sort of low-level dynamical systems to embed smart responses into systems. And then I'm really fascinated by contact and the way that contacts between multiple robots or contacts between robots in the world shape behavior. So I'm going to sort of touch on these three different areas of research in my lab as sort of glimpses of the kind of things that we're interested in. And the first one I want to focus on is in this area of compliance, using physical compliance of structures to adapt the behavior of robots, specifically in the context of manipulation and locomotion. And in this context, I'm really interested in how curvature can be used to control the mechanical properties of a robotic system. I'm sure everybody's familiar with if you take a paper roll tube and you try and bend it, it's relatively stiff. It's got a circular cross-section, has a high sort of bending strength in all directions. But if I put a pinch in that or if I fold it flat, it's got now a relatively soft response. And just by changing the geometry of the structure, not changing any of the material properties, we can modulate the stiffness property of structures that might find their way into robotics. We can do the same thing with structures that look like this, kind of like a U-shaped structure where maybe it has a strong direction of bending resistance, and if I flip it on its side, it has a weak direction of bending resistance. So focusing on the kind of tube aspect, one of the first things that we were interested in thinking about making adaptable and reconfigurable robot structures was, can we use this property of tubular structures where they have both a kind of strong component when they're in the circular cross-section shape and a weak component when you put a pinch into them to make reconfigurable structures that could maybe be, you can think of like a serial chain linkage where I can reconfigure where the flexures are within that linkage sort of adaptively. And one of our first approaches was just looking at tubes, taking tubes of different types of material and bending them, and trying to think about how we can actually impose bends in certain locations so that we can make, again, a serial chain linkage that has strong and weak elements, has struts and has or links and joints, and then how we can reconfigure the location of those links and joints. One way we created this, this sort of reconfigurable serial chain linkage that I thought was kind of neat was actually using flexible tubes and inducing a vacuum. If I take a flexible tube and I pull a vacuum, then there's a pinch that's going to form somewhere in that vacuum. Now, how do you control the location and the angle of that pinch so that I can control the location and angle of a bending joint? Well, if I put a little semicircular, ovalized shape across the tube and then I pull a vacuum, I bias it to bend in a certain location and a certain angle. And so by putting these cuffs along a flexible chain and then pulling a vacuum, we can very easily reconfigure where we have bending joints and what the angle of those bending joints might be. So we can, from starting with this sort of strong state of a circular cross-section shape, reconfigure it to be flexible in certain locations and have different kind of bending kinematics. So we played around with a kind of toy example of this where, just taking two of these cuffs, we can induce different axes of rotation in the same tube. And just by changing the orientation and location of these, we can just change the kinematics of their bending motion. We can couple more of these together to make multi-axis serial chain linkages that we can then change the direction of flexibility. These are all unactuated. You have to go in and you have to manually move the cuff to a certain angle. So, there's sort of some downsides to this. But it was an interesting way to sort of take a first approach at inducing these kinds of pinches, inducing basically flexible regions in what is inherently a sort of strong structure so that we can change the kinematics of this linkage, this multi-chain linkage. But like I said, this is all just done by hand. We go in and we change the location and then we push on it to observe the deflections. We wanted to extend this, and so our approach to extending this was, let's actually build modules that we can put inside of inflated tubes, so tubes that have a sort of strong cross-sectional shape, the internal pressure maintains their structural integrity. And when we inflate these tubes and they're at high pressure, we can then use a module that deploys within the tube that is completely self-contained, batteries, microcontroller, wireless communication. And that module can create a pinch in a location. That pinch then weakens the tube at that location. And then we can actuate along the joint axis that we've defined. So this now gives you the ability to have basically a backbone, a sort of strong backbone that we can then reconfigure the location of joints within that backbone and then actuate those joints specifically. And we explored this in the context of 1 and 2 jointed configurations. In the 1 joint configuration, which I'm just showing here, this is just 4 different placements of this internal actuation module. And we're just showing that we can basically fill out an entire hemispherical workspace with just 1 actuator just by reconfiguring its location and just actuating along the single axis that we choose. So we can get a high degree of mobility or manipulability volume within just this workspace using a single one of these modules. We did some other exploration of looking at locomoting versions of this as well, where we have 2 modules that kind of snake-like swim and move around and reconfigure their locations for different gates. But this is just a sort of example of the ideas that we have in terms of using a less is more approach to trying to make manipulators that have sort of high degrees of kinematic mobility, but using few actuators that can reconfigure on the fly so that we can sort of change the kinematics without having to have multiple redundant actuators at all times. And this was just a sort of initial dipping our toe into this world of reconfigurable manipulators. What I want to talk about is work that we've done more recently, which is, I acknowledge, has also been done by a bunch of people here at Stanford on using basically tape spring-like mechanisms to make manipulators and to make structures that we can reconfigure on the fly and manipulate in different ways. I'm sure everybody's familiar with the tape spring. Every lab should have one. Use it to measure things. It spools up into a very small volume. But tape springs have this amazing property that they can induce a bend. That bend is basically frictionless. I can move it at will to any location, doing it very, very easily. And then where that bend is connecting two struts, those struts can be both strong and soft. They have a strong and soft direction. And if I push on them in a certain way, I can get force application to things that I might want to grab onto. I can make potentially legs. I can do all sorts of interesting sort of mechanical interaction with the ability to both deploy this structure and to reconfigure the shape of that structure. And so this led to work building basically a planar manipulation device, a planar gripper, that uses two sets of tape springs. It is a bimanual gripper where it's formed from two triangular shapes, two triangular lengths of tape spring. We have the ability to control the angles of the tape spring and to unspool and spool both sides of each of the triangles. And that gives us a lot of really interesting kinematic control. So we can do things like translate through the workspace. We can hold a shape and then convey by basically unspooling one side and then spooling in the other side. And from those kinematics, we can do some very fun and interesting manipulation. So this is one of the first experiments we did several years back now. It looks like tape springs because we're literally just using tapes. Fun fact, I did find that you can buy tapes that don't have the numbers on them. It's a completely useless thing. It's very hard to find. And here's just an example of grabbing an object, conveying it, so maintaining the shape of the tape spring, conveying it and then twisting it and doing a kind of planar twist in hand, if you will. The tape spring has an inherent softness to it, again, because I can crumple it up, I can bend it, I can induce these sort of breaks in the tape spring's shape at any location. And that means, you have this sort of all the inherent safety of soft robotics. I can smash into things in the workspace, I can hit the tape spring. I can use obstructions to aid in my grasping and conveying objects. So by pushing, I don't have to squeeze as much, I can push into a surface and get an enhanced normal force in grasping. And so this sort of showed us that there's lots of really interesting opportunities with using these kinds of completely reconfigurable structures to make manipulators. Just using a single tape spring is kind of problematic because as you extend it out a long distance, it wants to fold in on itself. It's very weak in torsion. So to try and improve that, which you'll just sort of see in this next video, we made bidirectional tape springs. So you take two tape springs, you laminate them together, you allow them to shear with respect to each other, so you put them in a sort of low friction case, and then you tape around that. And that gives you now the ability to reach out longer distances without folding in on yourself. And it gives us the ability to pinch softly and to do interesting kind of fine scale manipulation. This is all teleoperated, by the way, I should say. And so we can do things like twisting, translating, conveying, multi-object conveyance. And all of this is using, again, the ability to spool and unspool material from the left and right side of each of the tapes. And then we have angle control that controls the sort of locations in the workspace that we translate to. I think there's one other video here. Yeah, conveying. So, freestanding conveyor belts is a sort of interesting application area of reaching out and then grabbing onto multiple objects. And we can lift relatively heavy objects as well. We submitted this paper, and it initially got rejected. One of the reviewers might be in the room. I have no idea. That's great. I mean, I applaud you. But I want to highlight reviewer 2 here. They gave us an amazing suggestion. They said one of the main limitations of the proposed system is that if I read it up here, the capability is only planar. And so it's limiting in that it only acts in the plane. If you could demonstrate 3D manipulation capabilities, this would be really great. And I want to highlight the review process as an important and useful thing because it pushed us to improve this robot. So we went back to the drawing board, or rather went to redesign this so that we can make it small enough to fit on a robot arm. Doing this, we had to make everything more compact, make it lighter so that we could hold it out at distance using one of our UR arms. From this then, we were able to show that we can use the same kind of ultimately planar, planar twisting and planar extending kinematics, but just reorient by this being attached to the end of a robot arm. Here you can explicitly see the spools of tape. So the left side tape, you can see it's unspooling and spooling out. And that's the sort of conveyance process where we're basically conveying tape out, pulling it back in. That allows us to twist and hold position. And this is, I think, picking a jalapeno. I went to buy more tomatoes, and they were out of season, and so I had to go to Home Depot and find some other plant that we could pick things off of. And so the idea is, like with these kind of deployable grippers, you should be able to reach through cluttered workspaces. If you hit something, it's not going to be problematic because they impart very low force onto the whatever you hit. They're not going to break by smashing into things. And then again, we get this sort of interesting capability of doing twisting, pulling, conveying. In this paper and work that I'm not showing here, we put a very simple force sensor on the tapes as well and show that just with a very simple PD servoing, we can do force control and rotate objects that are non-circular so that you adjust the width as you're kind of rotating this around. So this was very fun. I mean, this, I think, emphasizes one of the second point that I talked about with my lab. You know, this all started from us playing around with tape springs and asking, what can we do with this? And we stretched it out. We bent it in half. We started playing around with it as first an appendage for a swimming robot that we first published. But then we thought we can make a manipulator from this. And it sort of all came from this idea of play leads to purpose. From this work, then, our current version of this looks like the following. Instead of using just spools that we unspool and spool back so that you can deploy the appendage, now we have cyclic tapes. So basically take a tape, loop it back on itself, adhere it, coat it with a sort of messy TPU 3D printed structure that gives it some local compliance as well as some maybe sort of more textural friction, and have 2x2 tapes instead of just one tape so that we can kind of cage objects as we grasp them. And so this now, it doesn't have the capability of extending or retracting. It's got a fixed length. But we can do infinite rotation now. We don't have the limitation of how much tape is spooled up in any structure. We can grab objects and rotate non-circular objects very easily. There's no feedback control in this system. It's literally just the bending of the tape that's adapting to the different cross-section of the shape. In this video down here, we can grab multiple objects at the same time. We can do a kind of smush grab where we can push it up against objects and use the kind of frictional properties of the TPU skin to slide objects and try and pick them up. This is all sped up, by the way. This is, as you all know, very slow in the real lab. And from the 4 tapes, we can actually rotate in all 3 dimensions now. So we can do roll, we can do pitch, and then combinations of roll and pitch give you yaw as well. So this has been really fun. From initial forays into just playing with tapes in the lab led to us using just a single tape as a bimanual manipulator. That's now led to this interesting sort of infinitely rotatable structure that we can then grab multiple objects with, has all sorts of adaptive properties for the shapes of objects that it can grab. The TPU skin gives it much higher strength and pull-out force as we've characterized. And you get all the sort of, I think, nice adaptive properties of that soft robotics promise for grippers. What I think is really fascinating about tapes is that we get all those softness properties from a material that's inherently very stiff. And the geometry of the material gives you the sort of softness that we're really interested in. All of the kind of softness of these structures is really at this bend right here. When you grab onto something, it decreases in radius a little bit, and that decrease in radius gives you a very soft interaction with objects. So this is the first example of using reconfigurable and soft structures for making adaptive robots. Specifically in this context, grippers, but we've been playing with tapes in a bunch of different examples. I'm happy to talk about that after for the other kind of like ways we're exploring tape-based mechanisms. I'm going to change gears entirely. So I want to now talk about dynamics and the ways in which some inherent dynamics of biological systems and the way we can embed those into robots give robots very responsive and adaptive properties. This is a video I took during my postdoc. I was studying bee flight and building small robo-bee flapping wing robots. This is a bumblebee. It's at high speed. It's flapping its wings at around 180 hertz. And there's a very amazing property that small insects like bumblebees have. First off, they've got a very springy thorax. So they use their thorax kind of like a resonator. It's a spring mass system effectively. The wings are the mass, the thorax is the spring. And if you know anything about spring mass systems, well, there's multiple ways that we can generate oscillations in spring mass systems. And in biology, specifically, there's two ways that insects do it. The first way is, as you might expect, you have muscles that pull on the thorax. Those muscles pull synchronously, meaning the brain tells the muscle to contract, it contracts the thorax, and you do that once per wing beat, and you generate wing beats. There's a second way that insects generate wing beat oscillations, and these are the higher wing beat frequency insects, many of which we're most commonly familiar with: flies, mosquitoes, bees, anything that flaps its wings at above, let's say, 100 hertz. They flap their wings in a mechanism called asynchronous wing beat generation. Asynchronous means that the brain is only involved in generating the wing beats every 10 to 15 wing beats. And people have measured the neural activity from the brain going into the flight muscle. And for the most part, the wing is just flapping and the muscle is contracting without the brain telling it to contract whatsoever. Instead, the muscle of these insects has a special property that when you stretch it, it's got a delayed stretch activation. You stretch, and then after a short time, the tension rises to contract this muscle. And so for most of the time when mosquitoes, bees, flies are flapping their wings, the brain isn't telling the wing to flap. It's the stretch response of the muscle that is causing it to contract. And it's generating limit cycle oscillations because this is a system that is not under explicit time-based control from the brain. Super cool. This gives these insects all these adaptive properties that I'll talk about. If you clip their wings, their wing beat frequency changes immediately. If they smash their wing into something, the wing beat stops because you stop the stretch. But people hadn't really characterized the mechanics of the system until we started looking at it. We recently were able to show actually that there's a sort of change in the way people thought about the evolution of synchronous and asynchronous flight through this combined muscle physiology, new phylogenetics, new robotics work that sort of showed that synchrony and asynchrony can kind of be thought of on the same spectrum. I don't have time to talk about that, but it was really interesting work that emerged from this. What I do want to talk about is how we get this adaptivity and how we can use it in robots. So now I'm showing you a tension curve of one of these flight muscles. And what we should see is that the length is in the top there. I'm just doing a step change in length. I take a muscle and I pop it and pull it really quickly. And what I see is that there's an initial increase in the tension that wants to restore the muscle back to its rest length. That's that first little spike. And then there's a very slow transient rise of this force and then decay. And so all of the self-excited properties of asynchronous wing beats are from this delayed stretch activation. You basically get a sinusoidal excitation of this muscle, or if I pull this sinusoidally, the force lags the displacement, and when it lags it by enough that when the force is risen, I'm pulling back in, I get positive power work output from the system. You can think of delayed stretch activation as a low-pass filter. You've got the velocity of the muscle coming in, and then the muscle's force is just a low-pass filtered version of that velocity. And if you low-pass filter things, or if you induce time delays into things, we can get instabilities in mechanical systems, right? This is just an instability of flight. It's an instability in which you get closed-loop feedback, limit cycle oscillations. We can study these in a large-scale system so that we can sort of study the adaptive properties of them. And one of the things that we wanted to look at is how limit cycle oscillations of wing beats lead to adaptive wing beat frequencies as well as sort of interesting reactive responses of the wing beats. So what we wanted to do is set up limit cycle oscillations of a wing beat in a robotic system and then instantaneously change some mechanical property and see the response. In this case, we're changing the inertia of the system immediately. We're dropping a little weight on it. If you do this, you see there's an initial oscillation that the system's undergoing. We then change the inertia, and the system changes frequency and amplitude pretty quickly. All done just through the self-excited properties of the limit cycle, not through any kind of control that we're putting into this. We just set up this feedback loop and allow it to behave. And we did this for a bunch of different combinations of mass, and you can see if I plot it in this sort of esoteric way here of 1 over the emergent frequency squared versus the wing inertia, or vice versa, we see a linear behavior here. This is exactly the resonant frequency of the system, and we can see that basically when I change the resonant frequency of the system, the muscle is adapting to that new resonant frequency. And it does it inherently. We're not telling it to do it. It's just we set up the dynamics in the right way that it adapts. I plot it in this esoteric way because in the 1960s, people did this with bumblebees and go in and clip the wings of insects, change their inertia of their mechanical oscillator. They instantaneously adapt their wing beat frequency. And our argument is that this is happening through just the inherent delayed stretch activated process of the muscle, not through the brain, not through any sort of neural response that might be happening. Working with bees too, I saw another very cool response here. There's a little tripwire right here. This bee is going to run into it. It's flapping its wings at about 180 hertz. Within about 3 wing beats, it stops its wings. That's very, very fast. And it stops its wings through this collision. Well, we thought, if the stretch of the muscle is the thing that is contracting the next muscle and causing these oscillations, if I stop the stretch of the muscle, then I'm going to stop the oscillations. And so we asked the question, if I set up delayed stretch activated oscillations in a robotic system and then I enable a collision with an object, then what happens? Well, when you collide with an object, the wing beats stop, and then when you kick the system again, the wing beats start again. And so just through setting up a delayed stretch activation of our wing beats, we get inherent reactiveness as well. Collisions in the environment cause the wing beats to stop. They cause it to stop without any sort of sensory system on the wings. All you need to do is just stop the stretch of the muscle, and that stops the wing beat oscillation. And again, you get this sort of reactivity, the ability to respond to collisions without necessarily involving the brain and sensory systems. Now, of course, after a certain time, the bee knows that it's hit an object, it's sort of yawing out of the way. There's some neural response. I'll show you in our robotic system, there's no neural response. We're just setting up pure closed loop feedback systems that have the nice kind of adaptivity and reactivity that we want to sustain flight in complex environments. So I showed you kind of a large version of a robot there. But we've been working with smaller scale versions now. Versions that actually fly, we can fly them into cluttered environments and make them collide. This is just a DC motor-based robot. It's got springs that act as a kind of springy thorax. Interestingly, it's got a coupling mechanism to couple the left and right side wings. So we have independent left and right with an elastic coupling between them. It's sort of bio-inspired, but I don't have time to talk about that. All we're doing is just sensing the velocity of the motor, feeding that through a low-pass filter back into the torque of the motor. We don't have any encoders on this. We just measure the back EMF. Back EMF gives us velocity, and from that, we can just set up this self-excited flapping. This is what this looks like. This gives you a sense of how big it is. It's sort of moth scale. It can fly. It's passively stable with air dampers. It's not controlled. That's not yet the focus of this work. We're just trying to show flight capabilities and the reactive capabilities of the wing beats. But we can make this fly, and it can hover in place, again, passively through just passive air dampers that keep it stabilized. But one of the things we really wanted to show was how does this respond when wings collide with things? That was one of the reasons that we think delayed stretch activation is very nice for insects. It allows them to flap at high frequency without involving the brain, so they can just generate 1,000 hertz wing beat frequencies in some mosquitoes without having to send a 1,000 hertz signal from the brain. But also those wing beats can then be very responsive to collisions. And so we then flew this robot in cluttered environments. So here's an example. This is actually on guide wires so that it doesn't yaw out of the way of a collision. And we're just putting an object in front of the wing. You can see the wing stops. The right wing keeps going on because it's unaffected by this collision. The left wing stops. Now, I would contrast this with if we were sending in a sinusoidal signal. What you would see is that the wing would stop on the half portion of the sine, and then it would pull back, and then it would hit again, and it would pull back, and it would hit again, and it would pull back and hit again. Instead, it just stops and doesn't produce any torque. We measured the collisional forces and torques of this. And so it enables a kind of responsiveness for flight in clutter that we then were able to demonstrate through free flight experiments in a kind of challenging cluttered environment where this is an asynchronously driven flapping wing robot that is suffering constant wing beat collisions. And if we compare the sort of hovering height and the time of flight versus an adaptive delayed stretch activated robot versus a synchronous robot, we see it does much better when you drive it with this feedback responsive method of driving the wing beat actuation. So, this is another example of how I think very simple low-level dynamics can produce interesting adaptive and responsive properties of robots. It inherently can come from just these low-level feedback loops, and in biological systems, we actually think that's what's going on at sort of the fastest timescale of response of these flying insects is this thing that doesn't involve the brain. It's just purely a response of the muscle tissue. And it gives you interesting sort of reactive and responsive oscillatory behavior that can adapt to changing wing structure, to collisions, and things like that. And this has been a big collaborative project with folks at Georgia Tech who are neuroscientists and muscle physiologists in my lab, where we build robotic models of these things and do a kind of dynamical systems study of them as well. And I realize I'm racing right now, but I did want to get to everything I wanted to get to, so I'm sorry for that. I have one more section that I want to talk about now, switching gears entirely too. I'm sorry, I'm a little scatterbrained, but we like to play in my lab, and we have lots of different projects that I think are interesting and that I want to talk to you about. So the last one is I want to talk a bit about contact and how we can use contact for interesting collective behaviors, and also how contact shapes kind of, I think, odd responses of legged multi-contact systems. And that's the first one that I want to focus on here. So in a paper a couple years back, we had to change the title, but we wanted to call it Walking Like a Worm. And the reason we wanted to call it Walking Like a Worm is that when we looked at a bunch of multi-legged systems that have more than 1 foot in contact with the ground, many of the robotic versions of those multi-legged systems, not the ants, as they're walking, there's constant slip of their feet. If you watch this robot, there's basically no foot that's in static contact with the ground. They're always kind of slipping. And what we found is that when you model the dynamics of this right here, you find that it basically obeys the same mechanics of motion as this right here, this small swimming worm. Yet the contact forces of Coulomb friction are velocity independent. They basically just depend on the sign of the direction of motion and then mu mg. The forces of body interaction of this right here are velocity dependent. A viscous swimmer exerts forces on the environment that then exert back on it velocity dependent forces. So how do you get something that has effectively a velocity dependent like behavior in its net contact forces that look like this, yet the intrinsic force of interaction is speed independent? And this really fascinated me because, again, this is the fundamental, statement of question. If I have a single static point of contact that is moving at velocity v, then in a viscous fluid, I should have a reaction force that is minus v with some coefficient, right? I get a viscous force that's resisting me. This is viscous force. This is what a worm experiences when it's swimming. This is Coulomb force, Coulomb friction. The basic version of Coulomb friction, ignoring static friction, ignoring anything else, ignoring Strybeck, all that kind of stuff. If I slide or if I push with a velocity v, I get a force that's reacting at me, mu mg. There's no velocity component in there whatsoever, except for whether I'm pushing in this direction or this direction, right? Completely flat, I can move at different velocities. I'll get the same frictional response. If I make one of these contacts active, meaning like a wheel that I start to spin, well, a wheel in a viscous friction context can change the location of this force velocity curve. I can shift it to the right or left. And where that curve crosses zero, that's where the force acting on my system is zero. That means I'm at equilibrium. That's my equilibrium speed that I would move at. If I do this in Coulomb friction, it just shifts the location of this step function, this Heaviside function, right? My equilibrium speed should be right there where the force crosses zero, and that's exactly what the contact speed of this wheel would be with contact with the ground. If I'm a worm, if you will indulge me in making a worm a bunch of active wheels that are all moving at different speed, I'm sorry. This is where the physics in me comes in, I guess. Then in a viscous context, a bunch of wheels that all have velocity-dependent forces that are different velocities still are just a bunch of lines that add together, a bunch of lines that add together, just another line, right? So this should look just like this. What happens in this case when I have a bunch of Coulomb friction elements that are acting at different speeds? This is the case of a multi-legged system that is walking, or a snake that's gliding on the ground. I have velocity-independent friction, but I have a bunch of these elements that are at different speeds. So we built the world's dumbest robot, maybe? I don't want to be judgmental. This was an undergrad made this amazing robot. It's a carousel. It spins indefinitely. It's got a nice little slip ring in there so we can spin infinitely. And the goal of this wheeled robot is it has 10 wheels that all move at different speeds. So I'm going to put in 10 different speeds into the system. I'm going to let it reach equilibrium. This is my version of a walking robot. And I'm going to ask, what speed does the system move at? And this is a thought experiment I really like playing with people, so I'm curious if anybody will let this play. You can think about this. Some of the wheels are moving at fast speeds, some of them are not moving at all. And if I just order all 10 speeds from lowest speed to highest speed here, what is the net rotation speed that the system will move at? Anybody have any guesses? In the viscous case, it would be the mean of all those speeds, because I add up all of them and I divide by the total number of contact points and I get the mean. But when I'm adding up Coulomb friction systems, it's the median. Just means it's this speed right here, right? If I got a set of 10 elements, the median is just the one that's in the middle, right? And what are medians useful for? Well, medians are cool because they exclude outliers. I could have a wheel that's spinning at, I don't know, 1,000 radians per second, and it won't affect the rest of them. It won't affect the median. I can make omega 10 1e5, the rest of them the same. The system's still going to spin at the same speed. So that's kind of cool. Medians are interesting because of that. The other thing that they do is, if we think about the way this is working, I'm effectively adding up a bunch of step functions here across my wheels from slowest speed to highest speed, and I can build almost arbitrary force velocity curves from these multi-contact systems. We measured the ground reaction forces of our system. This is when all the wheels are moving at constant speed, so it should just look like a wheel. It's kind of steppy, if you will. And then we varied them linearly from slowest to fastest, and this is what our expected force velocity curve would be, and that's the measured force velocity curve. So speed-independent friction, when you have multiple contacts that move at different speed, can look like worm-like viscous friction. Why did our original analysis of multi-legged systems that are slipping look like it's walking like a worm? It's because the overall frictional force looks viscous, because at any point when you have contacts at different speeds, you get these very complex very complex additions of all of these step functions. Yeah?
How do you ensure that it's just Coulomb friction? I feel like a lot of contacts maybe also have some linear friction as a combination of those two.
I mean, we only in the sense that we characterized it by basically holding it in place and running all motors across a range of speeds and showing that the ground reaction force is the same. Beyond that, yeah, I mean, after doing these experiments for a long time, you get a buildup of plastic on there. Humidity and things like that can change that, sure. But we just did it empirically and showed that over the range of speeds we were studying, it's speed independent. This is just a simulation of a 40-legged walker making foot contact or no contact. This is what the instantaneous force velocity curve looks like for this. Again, you're just taking a bunch of step functions and adding them together. But it's very much not just a speed-independent step function. It's this complex thing. And if you look at it on a gate average basis, you now get these kind of viscous-like forces that emerge from speed-independent friction. I keep saying speed-independent, by the way. It's a step function. It's dependent on speed. It's just dependent on whether you're above or below the contact speed. So this is really cool. Okay, we kind of confirmed that when you have snake-like locomotion where all the contacts are moving at different speeds, when you have multi-legged systems that are all slipping, we get kind of weird, interesting frictional behavior. There's something else that's cool that popped out of this, though. Let me actually preface this with, there's interesting properties of medians. If I give you two numbers, 1 and 2, in a set, what's the median of that set? It's either 1 or 2, or it's anything in between 1 or 2. Any even set can possibly have a range of values where there is no well-defined median. It's just a range of medians. So what if I make 5 wheels move forward and 5 wheels move backwards? I've got positive 1 meter per second and negative 1 meter per second. What's the median value of that set? It's 0, it's 1 meter per second, it's 0.5, it's somewhere in the middle. What this means is that if you drive these wheels in opposite directions, you can create regions where you have 0 friction, because they're constantly breaking friction against each other. So they're constantly pushing against each other. I can measure the ground reaction forces here, and there's a big swath of regions here where if I slide in that intermediate friction speed, I experience zero friction on my body, theoretically. Let me show you an example. So this is the system. We're going to use our favorite thing, which is a tape measure, as a kind of compliant element, just to show we're pushing on this. It's not moving. It's, generates high friction with the ground when it's not in motion. And then I'm going to put 5 wheels into forward motion and 5 wheels into backwards motion. And it shouldn't move anywhere if I do that, by the way, right? I mean, if I turn them all and they're equal and opposite forces, it doesn't move anywhere. But if I give it the slightest touch, it slides. And it'll slide indefinitely because we made a zero friction surface here. Because I'm constantly breaking friction in the positive and negative direction. I can glide it that way, I can glide it this way. It's amazing to play with. And it's so fun because of the slip ring. You can just spin this thing continuously. And we actually showed that by turning on and off different numbers of active contacts, we can modulate the coefficient of friction. So I can make this thing drive, and then I can make it slide by turning on 6 of them forward and 4 of them backwards. So now the coefficient of friction is some subset, some smaller value than what all 10 of them would produce if they were just sliding. And we can do it linearly through this sort of modulation of active control. This is just an example of how did we come to this point here of creating a frictionless surface and sliding? I mean, we were led to this by a question that we initially thought from multi-legged slipping robots that kind of look like worms. We then wanted to look at what is the mechanics of these multi-contact systems, and it led us to frictionless substrates that do interesting things. I think with that, we're just about at time, right?
Getting there, yeah.
Getting there, okay. Well, getting there, I'm going to show, oh yeah, please.
So, is it only frictionless on its rotation? Can you move it? Is it
It's fantastic. If I try to make a planar version of this where I can create frictionless directions of movement, we haven't done that. I think that's a great question. That I think is possible, but I haven't done. Yeah, it's a good question. I mean, maybe with casters on the structure so that it can always locally reorient the wheels. I think in the interest of time, I'm going to stop because I've got another section, but we can talk about it after. So let me just pull up again my thank you. So again, compliance, dynamics, contact, and I want to say thank you. And please sign up for the Mesh RCN. We will be sending out information about that periodically. Thank you. Yeah, please.
On the adaptive wing beam, I don't know if there's an application when the V hit the tripwire, both its wings, when your robot hit the tripwire, only one wing stops. I mean, I guess because when the V's wing stops, it falls. But what's the?
Yeah, it's a great point. So, two answers to that. The first is in the insect, at least in flies, people have studied this. The left and right pairs of muscles are undergoing this self-excited oscillation. The thing that couples them is not the brain, it's a mechanical structure in the body. And people have cut that and shown that the wings will then go out of sync. So with the bees, likely is the coupling between the left and right, the elastic coupling between the left and right is different than in our robot. In our robot, we do have an elastic coupler that is coupling the left and right, and when we take that out, the wings dephase and unsync. If you make that stronger or weaker, you'll get, stopping this one will have lower amplitude or higher amplitude.
I have a question about the zero.
The world's worst robot, yeah.
How sensitive is it to starting up the motors at the same time? It seems like maybe not a super precise system.
It's not, no. And there's tons of backlash and then slop.
It didn't move a millimeter until you pushed on it. I was just sort of surprised that it didn't have some wiggliness.
When we do run this for longer periods of time, you'll see it'll start to drift in certain directions. And I think that's because there's some parts of the ground and parts of the wheels that have slightly higher friction, and if they all catch at the same time, it'll kick it in certain directions. So theoretically, zero friction doesn't mean practical zero friction. The one thing I was gonna say, no, I lost my train of thought. Yeah, that's all I was saying.
And then I also had a question about the tape grippers. I'm just curious about the number of different and types of objects that it can successfully manipulate. I'm just sort of thinking about like the Amazon picking challenge. And people have tried a lot of different grippers there, but this seems like a really, really good one. Have you tried it in those types of environments where you're trying to pick up a lot of different things?
No, I should, right? I think the first version that is this extensible gripper, so not the cyclic one. The challenge with that is that its point of contact is just a point. It's these two, convex ovals, and so it's pretty limited in the type of shapes that it can grab onto without them falling out. The second one, I would love to put it in some, blocky type bin picking challenge and see how it performs. We haven't published that yet. We're still working on it. So I think.
Yeah, it's like if it could pick up things in plastic bags, and I imagine it would be pretty good at that.
I think it speaks to that as hopefully play turning into purpose in the sense that we've demonstrated interesting things, but now we want to find a real purpose for it.
Guard of it. You said that you couldn't cause it to extend or retract because of that shape, but couldn't you have bent it in the center of the bend and then use kind of the force of it pushing on separately to kind of allow it to move inward and outwards, kind of like almost like a slinky style?
Oh, interesting. Almost like a sling. I see. So you're saying use the
like if you push it inwards, right? Mm-hmm. Because of the force of the outer bands, that will keep it inward. It's hard to explain. And then by moving the conveyor belt inwards and outwards, you could also still get that kind of extension you were showing.
I think we'll have to sit at a whiteboard after this, but what I will say is we did think about trying to extend that version. What you can do is, it's just a loop, right? There's no reason I can't translate the whole loop back and then translate the whole loop out. Well, there's a reason. It makes the actuation harder because you have to actuate both sides instead of just one side. But yeah, I think it's two different sort of archetypes of like these grippers. One's cyclic, constant length, one's deployable. Yeah.
I was wondering if there are certain tasks that the tape grippers can do, but like a standard hand gripper could not.
I'm absolutely no expert in manipulation. I have absolutely no experience in it whatsoever. I sort of backed my way into this. So I would say I don't know. The claim that we made is that it's a structure where the manipulating surface is the entire length. So that was one. And then the ability to do twisting over multi twisting twisting objects many times in constant contact is the other novelty that we thought we landed on. Again, please somebody after tell me how I'm wrong. I'm happy to hear that. But yeah.
I actually have a follow-up on that one. When I look at, so you show demos of the tape gripper picking up fruits to harvesting. I feel like that's a perfect application for this type of hand. And I look at many agricultural robots. They do harvesting with either pedal grippers or suction cups, but they all have all kinds of limitations. Like for grippers, it's really hard to reach into connector region, and if you do so, your arm needs to be really long. The whole system can be pretty heavy. And when I look at your design, it has the whole thing is very compliant. The whole thing can be very gentle, will not cause easy damage to the thing you are harvesting, and you can reach into small space. And since it has sufficient grasping, especially after you put rubber rings on top of that. So I can't find a reason why it is not the best gripper for harvesting, and I wonder. I wonder, have you thought about actually putting it into more application, and what are the actual limitations?
When I talk to people in agriculture, they say we don't need to be that delicate for many of the things that we harvest. We can go in and suction cup and clip, or we can shake the tree. This is, it's capable of, I think, quite nice fine scale manipulation. Teleoperated, by the way. Getting into a point where we're doing this autonomously might be a challenge. But they say that there are certain crops that are sort of very hard to. There's a term for it, and it's escaping me right now. But basically, exotic fruits where you want to go in and you not want to damage it whatsoever, and it needs to be twisted off. And I'm forgetting now the specific name for that. But so I think there's niche applications. I don't think this is like the new thing that's going to basically solve all agricultural harvesting.
Luxurious agriculture tool. The people can use for like expensive fruits like that.
Exactly. That's what I've heard, is that there might be niche applications.
Cool. Any other questions?
I'm around after, by the way, so you know.
Let's take maybe 2 more minutes for questions. Maybe we'll get one Kukoski group and then one in the back.
Sure. Yeah. Yeah, sure. I want to ask a question about the adaptive wing beating and sort of this idea that the delayed stretch activation was really cool. And I guess you were explaining that in the insects, they use that so you don't have to send, signals at thousands of hertz. Do you see this in other animals that maybe move slower, sort of an adaptive mechanism for like legged robots? Is there insects that use this for locomotion? Can this apply to something besides building tiny flapping robots, I guess, and where do you see that?
Yeah, so there are stretch responses in other types of muscle. I think certain types of cardiac muscle have a stretch-like response, but for the most part, this specific self-excited oscillation we've only seen in insects. We haven't looked at it elsewhere. It is, I think the primary thinking is that it's helping to solve the kind of fast wing beat problem, but there are like 20 hertz insects that still use DSA. So it doesn't necessarily mean that it's only the high wing beat frequency ones. But yeah, so the mechanisms of it and the why are still kind of open questions in biology.
There was one more in the very back.
I'm curious about the flexible wing design for aircraft, and if that has any relevance in your perspective on the second area of research with adaptive wing beat.
You know, the wing flexibility in that is all basically chosen so that we get appropriate pitching at the frequencies we're working at. We don't really do anything in terms of thinking about like beyond just a flexing of a hinge, what's going on within the wing membrane itself. So maybe, but I don't know.
So let's thank Professor Gravish.